Light is the most studied phenomenon in the history of science. We've built lasers, fiber optic cables, telescopes, MRI machines, and nuclear reactors around our understanding of it. We've used it to measure the age of the universe, confirm Einstein's relativity, and send information across the planet at 299,792 kilometers per second. And we do not know what it is. Not in the philosophical sense. In the physics sense. After 224 years of experiments, 100 years of quantum mechanics, and a 2025 experiment at MIT that was supposed to settle the question once and for all, we still cannot explain how a single photon of light decides to behave as a wave or a particle. We can describe it. We can predict it. We can use it. But we cannot explain the mechanism behind the choice. And in July 2025, MIT proved that the mystery is even deeper than Einstein or Bohr imagined. Everything you thought you understood about light is wrong. And the truth is the most beautiful unsolved problem in all of physics. Here's what they taught you in school. Light is an electromagnetic wave. It travels at the speed of light, obviously, and it has a wavelength and a frequency. Red light has a long wavelength. Blue light has a short one. When it passes through a prism, it separates into a rainbow. It bounces off mirrors. It bends through lenses. Wave. Simple. Done. Except it's not simple. Because in 1905, Albert Einstein, the same Einstein who would go on to describe how gravity warps spacetime, published a paper showing that light is also a particle. Specifically, he showed that when light hits a metal surface, it doesn't release electrons in a way that waves should. It releases them in discrete packets, as if the light were composed of tiny bullets, each carrying a specific amount of energy. He called these packets quanta. We call them photons. This was the birth of quantum mechanics, and it created a paradox that has haunted physics ever since. Light is a wave. Light is a particle. Both of these statements are experimentally verified. Both are true. And they are, classically, mutually exclusive. A wave is spread out. A particle is localized. A wave diffracts and interferes. A particle has a definite position and trajectory. Something cannot be both at the same time, and yet light is. This is wave-particle duality. And the experiment that demonstrates it, the one that Feynman called the central mystery of quantum mechanics, is the double-slit experiment. The double-slit experiment is so simple it's almost insulting. And that's what makes it terrifying. Take a light source. Shine it at a barrier with two thin parallel slits cut into it. Behind the barrier, place a screen, a detector that records where the light hits. If light were purely a particle, little bullets being fired at the barrier, you'd expect two bright bands on the screen, one behind each slit. Bullets go through the left slit, hit the screen behind the left slit. Bullets go through the right slit, hit the screen behind the right slit. Two bands. Simple. But that's not what happens. What you see is an interference pattern. Alternating bright and dark bands spread across the screen, a pattern that can only be produced by waves. Two waves passing through the two slits spread out on the other side. And where the peaks of one wave align with the peaks of the other, you get constructive interference, bright bands. Where a peak meets a trough, you get destructive interference, dark bands. Cancellation. The light erases itself in certain places. So light is a wave. Case closed. Except it's not closed. Because here's where the experiment starts breaking reality. Turn down the light source. Way down. So low that you're sending individual photons, one at a time, through the apparatus. A single photon. One particle. It approaches the barrier. It passes through which slit? One of them, presumably. It's a single particle. It can't go through both. It hits the detector screen. A single dot. One point of impact. Particle behavior. Fine. Now send another photon. Another, then another, then another. After hundreds, then thousands, then millions of individual photons, each one passing through the apparatus alone, you look at the accumulated pattern on the screen. And it's the interference pattern. The same wave-like distribution. Bright bands, dark bands. An interference pattern produced by individual particles, each arriving one at a time, each hitting the screen at a single point, but collectively forming a pattern that is only possible if each individual photon somehow interfered with itself. As if each photon passed through both slits simultaneously, behaved as a wave, created an interference pattern with itself, and then collapsed into a single point when it hit the detector. One photon, both slits, wave and particle, at the same time. Your brain is screaming right now that this makes no sense. And you're right. It makes no sense in classical physics. In quantum mechanics, it's the foundational observation, the starting point, the thing we've been trying to explain for a century. And here's where it gets truly maddening. Suppose you try to be clever. You add a detector at the slits, a device that can tell you which slit each individual photon passes through, left or right. Simple measurement. Now you'll know whether the photon goes through one slit or both. The moment you do this, the moment you measure which slit the photon passes through, the interference pattern vanishes. The photon behaves as a particle. It goes through one slit. It hits the screen behind that slit. No wave behavior. No interference. Two bands. Particle. Stop measuring. The interference pattern comes back. Wave. Measure. Particle. Stop. Wave. Measure. Particle. The act of observation, of acquiring information about which path the photon takes, changes what the photon does. Not because the detector disturbs it physically, not because you're bumping it with another particle, but because information about its path becomes available. The universe behaves differently depending on whether or not something knows which slit the photon went through. This is the measurement problem. It's the heart of quantum mechanics. And after 100 years, we still don't have a consensus explanation for why it happens. We have interpretations: Copenhagen, many worlds, pilot wave, quantum Bayesianism, relational quantum mechanics. But they're interpretations, not explanations. They're different stories we tell about the same math. The math works. The predictions are flawless. But the meaning, why does observation change reality, is the open wound at the center of physics. All right, I need you to lock in right now. Because what I'm about to show you involves an experiment from 2025 that was supposed to settle this debate, and instead made it deeper. Here's the question. When the photon in the double-slit experiment seems to go through both slits at once, do you think the photon literally passes through both slits as a spread-out wave? Or do you think the photon goes through one slit, but something else, something we don't understand, creates the interference pattern without the photon literally being in two places? Drop a rocket if you think the photon literally goes through both slits. Drop a collision if you think something weirder is happening. Lock it in. Because MIT just tested this, and the answer is more unsettling than either option. Theory A, the standard quantum view. The photon passes through both slits simultaneously as a quantum superposition, a wave function spread across both paths. There is no fact of the matter about which slit it goes through until it's measured. The wave function is the complete description of reality. When you measure, the wave function collapses into one outcome. This is the Copenhagen interpretation, and it's what most textbooks teach. It works mathematically, but it requires you to accept that an unmeasured photon has no definite position, that it genuinely exists in a superposition of being in two places at once, and that measurement itself causes a physical change. Many physicists find this deeply unsatisfying, because measurement is never precisely defined. When does it happen? What counts as a measurement? A detector? An atom? A conscious observer? Theory B, pilot wave theory. The photon is always a particle, a real, localized object with a definite position at all times. But it's guided by a pilot wave, a real physical wave that passes through both slits, creates an interference pattern, and steers the particle along one specific path within that pattern. You get interference because the wave goes through both slits. You get a dot on the screen because the particle goes through one. The wave is real. The particle is real. No superposition. No collapse. No mystery. It's elegant. It's deterministic. It reproduces all the predictions of standard quantum mechanics. But it requires a hidden variable, the pilot wave, that we've never directly detected. And most mainstream physicists abandoned it decades ago in favor of the Copenhagen interpretation, largely for historical and sociological reasons rather than experimental ones. And then MIT entered the chat. In July 2025, a team led by Nobel laureate Wolfgang Ketterle at MIT performed the cleanest, most precise version of the double-slit experiment ever conducted. And they did it in a way that goes straight to the heart of the Einstein-Bohr debate. Here's what they did. Instead of using physical slits cut into a barrier, which are messy, imprecise, and involve billions of atoms, They used two individual rubidium atoms as the slits. They cooled more than 10,000 atoms to near absolute zero and trapped them in an optical lattice made of laser light. Then they isolated two individual atoms, separated by a precise distance, and used them as scatterers. A single photon from a laser hits one or both atoms, scatters, and the scattered light is captured by an extremely sensitive camera. The atoms are the slits. Two atoms, two possible scattering sites. And the photon's behavior, wave or particle, depends on what happens to the atoms when the photon scatters off them. Here's the critical insight. When the atoms are tightly trapped, held firmly in place by strong laser fields, they can't move. They can't recoil. And because they can't recoil, there's no way to tell which atom scattered the photon. No path information exists. In this case, the photon shows wave behavior. Interference fringes appear on the camera. But when the trap is loosened, when the atoms are allowed to jiggle, a scattered photon can give the atom a tiny kick, a recoil. That recoil carries information about which atom did the scattering. Path information now exists, encoded in the motion of the atom. And when that happens, the interference pattern vanishes. Particle behavior. The crucial part, the part that killed Einstein's objection, is that the experiment didn't use Einstein's imagined spring or mechanical detector to measure the photon's path. It didn't use any external device at all. The path information was encoded in the quantum state of the atom itself. The mere existence of which path information, whether or not anyone looked at it, was enough to destroy the interference. As Vitaly Fedoseev, a postdoc on the team, put it, the springs do not matter. What matters are quantum correlations between photons and atoms. Einstein believed you could, in principle, build a device clever enough to detect which slit the photon passed through without disturbing its wave nature. He was wrong. MIT showed that the issue isn't the device. It's the information. If which path information exists, anywhere in the universe, encoded in any system, whether or not a human observes it, wave behavior disappears. The universe keeps its books, and it will not show you both entries at once. And that brings us to the experiment that pushed this even further, into territory that sounds like science fiction. In January 2023, a team at the University of Science and Technology of China, led by Chuanfeng Li, published a paper in Light, Science and Applications demonstrating that they had successfully separated the wave and particle attributes of a single photon. Using a concept called the quantum Cheshire cat, named after Lewis Carroll's cat that can separate its grin from its body, they created a situation where a photon's wave-like property traveled along one path through an interferometer, while its particle-like property traveled along a different path. The wave went one way. The particle went the other, like peeling the smile off a cat and sending it to another room. They achieved this using a combination of pre-selection, post-selection, and weak measurement, a technique that extracts a tiny amount of information from a quantum system without collapsing its state. And the results were consistent. The wave attribute of the photon, its ability to interfere, was localized on one arm of the interferometer, while the particle attribute, its ability to be detected as a click, was localized on the other. This doesn't violate quantum mechanics. It's predicted by the formalism, but it does something deeply unsettling to our intuition about what a photon is. Because if the wave and particle attributes can be spatially separated, sent to different locations, then neither attribute is the true nature of the photon. The photon is something else, something deeper, something that has properties we don't have a name for, which manifest as wave-like or particle-like depending on the situation. And that something deeper, the thing that a photon actually is, beneath the wave-particle duality, is the attribute of light that science still cannot explain. Now let me connect all of this, because here's where the pieces come together into something genuinely profound. In 1801, Thomas Young showed that light behaves as a wave. In 1905, Einstein showed it behaves as a particle. In the 1920s, Bohr and Einstein debated whether both natures could coexist, and Bohr argued they could, but never simultaneously. For a century, this was the accepted wisdom, complementarity, wave or particle, never both at once. In 2023, a Chinese team separated the wave and particle attributes of a single photon and sent them to different locations. The photon was being both, but the both was distributed in space. Complementarity held locally but was violated globally. The wave was here. The particle was there. The photon was everywhere and nowhere. Then in July 2025, MIT performed the cleanest double-slit experiment in history and confirmed that the destruction of wave behavior isn't caused by a physical disturbance. It's caused by the existence of information. Not observation. Not consciousness. Information. If the universe contains a record, anywhere, of which path the photon took, the wave dies. Erase the record. Make it fundamentally inaccessible, and the wave returns. Light doesn't care whether you are watching. It cares whether anything in the universe could, in principle, determine what it did. And it adjusts its behavior accordingly. This is not a metaphor. This is the experimentally verified behavior of photons in 2025. And nobody, not a single physicist alive, can explain the mechanism by which this happens. We have equations that predict it perfectly. We have interpretations that tell stories about it. But the underlying mechanism, how does the photon know whether information exists? How does it choose between wave and particle? Is entirely unknown. And this connects to you in a way that isn't abstract at all. Every piece of technology you use that involves light, your phone screen, your Wi-Fi, your fiber optic internet, your camera, your medical imaging, your solar panels, your laser eye surgery, works because we can predict how photons behave. The math is perfect. The engineering is flawless. But we're engineering with a tool we don't understand. We know what it does. We don't know why it does it. We're building a civilization on a foundation whose deepest nature is a mystery. And here's what makes it existential. Quantum mechanics, the framework built on wave-particle duality, isn't just about light. It governs everything. Electrons, atoms, molecules, your DNA, the chemical bonds that hold your body together, the nuclear reactions that power the sun, the quantum fluctuations that seeded the large-scale structure of the universe. Everything that exists is governed by the same formalism that says a photon can go through two slits at once, and that observation changes reality. You are made of quantum objects. Every atom in your body obeys the same rules that make light behave impossibly in the double-slit experiment. The mystery isn't out there. It's inside you. So here's the question I'll leave you with. And this one has genuinely kept me up at night. For 224 years, we've been asking, is light a wave or a particle? And the answer, confirmed by the most precise experiment ever conducted in 2025, is neither. Light is something else. Something that can manifest as a wave or a particle. Something whose wave and particle natures can be physically separated and sent to different locations. Something that adjusts its behavior based on whether information about its path exists anywhere in the universe. We don't have a word for what light actually is. We don't have a concept for it. The closest we have is the wave function, a mathematical object that describes probabilities. But is the wave function real? Is it a physical thing that exists in nature? Or is it just a tool, a calculation device, that gives the right answers for reasons we don't understand? If the wave function is real, then reality is far stranger than anything we can visualize, a vast, multidimensional space of superpositions and entanglements underlying the solid world you experience. If it's just a tool, then the actual nature of reality is completely unknown, and quantum mechanics is an extraordinarily successful operating manual for a machine whose inner workings are invisible to us. Either way, the most fundamental thing in the universe, light itself, is something we cannot explain. And the most honest thing physics can say, after 224 years and the cleanest experiment in history, is, we don't know what it is. Is that humbling or terrifying? Tell me in the comments. If this video made you question the nature of the light hitting your eyes right now, if you want to keep going deeper into the mysteries that are hiding in plain sight at the foundation of reality, hit the subscribe link in my bio right now. Subscribe to the channel. Because next week, we're covering what happens when Earth's magnetic shield fails, the geomagnetic reversal that killed the Neanderthals 42,000 years ago, and the 2026 study that showed it can last not 10,000 years, but 70,000. I'll see you there.